This is Learning Assessment Problem 812. The problem-solving strategy here is that of combining complex impedances and admittances and working with a phasor diagram. The circuit consists of two parallel impedance elements connected to a current source. And we are to determine various currents in this circuit, a voltage, and then plot those results in a complex phasor diagram. So the phasors which we'll be looking for are the current source, which is given in the problem, the voltage developed across the two parallel elements, and the currents flowing in those impedance elements I1 and I2. We'll call the 2 ohm resistor impedance Z1 and the 4 ohm impedance in the capacitor Z2. So Z1 will equal just a resistive So Z1 will equal just the resistance of 2 ohms. Z2 is the impedance of the capacitor, and this is equal to minus J4 ohms. Since these two impedances are in parallel, it will be easier to discover their Since these two impedances are in parallel, we will convert them to admittances in order to simply add the admittances to determine the effect of the two elements in parallel. So Y1 will equal 1 over Z1, and this will be 0.5 Siemens, or the units for the admittance. Y2 is equal to the reciprocal of Z2, and that is equal to J 0.25 Siemens. For the two elements in parallel, we can say that the total admittance YT is equal to Y1 plus Y2, and this will be equal to 0.5 plus J 0.25 Siemens. In the polar form, YT is equal to 0.559. In the polar form, YT is equal to 0.559 at a phase angle of 26.57 degrees. And this would be equal to the reciprocal of the total impedance connected to the current source. So now we can say that the voltage across these parallel elements will be the current divided by this YT, or that's equivalent to ZT times the current. Or that is equivalent to ZT times the current. At any rate, V is equal to 4 at an angle of 45 degrees. The result is V is equal to 4 at an angle of 45 degrees for the current divided by 0.559 at an angle of 26.57 degrees for the impedance. Now we will calculate the voltage V. This will be equal to the current I divided by that total admittance YT. This is equivalent to the impedance ZT times the current. And this is equal to 4 at an angle of 45 degrees for the current divided by 0.559 at an angle of 26.57 degrees for the admittance. And this is equal to 7.155 at an angle of 18.43 volts. Now we can calculate the two currents flowing in the impedances. We'll have I1 is equal to Y1 times the voltage V. This is equal to 0.5 Siemens times 7.155 at an angle of 18.43 degrees volts, or I1 is equal to 3.578 at an angle of 18.43 degrees amperes. I2 is equal to Y2 times V, and this is equal to minus and this is equal to J 0.25 Siemens times V, and this will be equal to 0.25 at an angle of 90 degrees times V, or I2 is equal to 1.789 at an angle of 108.43 degrees amperes. So we can summarize those results. V is equal to 7.155, an angle of 18.43 degrees volts. Next we can go on and put these elements. Next we can proceed to put these phasor representations in the phasor diagram. The result is shown here. The way this is performed, we have the real axis, the imaginary axis for the phasor diagram, and then we just have to use a protractor perhaps to get the appropriate angle with respect to the positive real axis and scale the length in some fashion. So we have the three currents shown. Notice that the current I1 is in phase with the voltage V. That's the current through the resistor, whereas the current I2 leads the voltage across the circuit by 90 degrees. So we have some observations about this phasor diagram representation. As we said, I1 is in phase with V1. As we said, I1 is in phase with V. As we said, I1 is in phase with the voltage V. We have I2 leads V by 90 degrees. And we can also observe that if we add the phasors or vectors I1 plus I2, this is equal to the current I, and this represents the Kirchhoff's current law of behavior, the summation of two currents equaling the third.